Hi, my name is Christopher Eilif Sprague. I'm a PhD student at KTH Royal Institute of Technology in Stockholm, Sweden, working on robotic planning within the Swedish Maritime Robotics Center. In this presentation, I'm going to talk about our work on using reinforcement learning for informative path planning in bathymetric environments, which is essentially learning to learn bathymetry. So first, I'd like to start off by stressing the importance of autonomous underwater vehicles, like this one pictured here, Sweden's Hugin vehicle, RAN, near Thwaites Glacier. Because AUVs are autonomous and capable of gathering data in inaccessible environments, they're particularly well suited to exploring unknown regions, such as under ice shelves. Due to this, they are key enablers to furthering our understanding of oceanographic phenomena. And although the data gathered by AUVs pertains only to local regions, the ocean is a globally connected system, and the reduction in uncertainty in these unknown regions has implications in global models. For example, in estimating sea level rise or modeling thermohaline circulation. Since this data is so important, it is paramount to make sure that enough detail is captured to ensure the accuracy of the resulting oceanographic models. With multi-beam echo sounder surveys from ships, we can get a broad sense of what is there. However, there's a lot of detail left to be elucidated. With AUVs, we can get a much closer look, as shown in these images from the RAN AUV. However, depending on the variation of the bathymetric surface, different areas may not require the same amount of detail to accurately capture the characterization. Hence, we could spend less time surveying monotonous areas and more time in areas which have a richer characterization. In inaccessible and unknown environments, this requires adaptive online planning. In practice, most AUVs execute pre-coordinated plans, which are based on our expectations of the environment. Of course, in areas in which we already have a broad ship survey, we may have a reasonable expectation of what is there. However, in inaccessible and unknown regions, such as under ice shelves, how good can our expectations actually be? To circumvent this predicament altogether, the AUV should be able to develop its own expectation of the environment as it gathers data, and plan accordingly to improve its understanding of the environment. This capability describes what is known in literature as informative path planning, which asks the question, how should I navigate, given my expectation of the environment, to improve my understanding of it, while respecting resource constraints like limits on, for example, time or battery usage. Most informative path planning approaches use Gaussian processes to quantify this expectation and understanding of the environment. In these approaches, acquired data is used to update the Gaussian process model as the vehicle moves throughout the environment and gathers data, similar to what is shown in this figure, where added data updates the model. An issue that many informative path planning approaches have had to reckon with is the well-known fact that conventional Gaussian processes struggle to regress large data sets due to their cubic complexity with the number of data points. Another class of Gaussian processes that many approaches have used to ameliorate this issue is sparse Gaussian processes, which use inducing points to sparsely approximate the dataset, reducing the complexity to nm squared, where m is the user-defined number of inducing points. However, despite this improvement, the complexity still scales with the dataset size. To address this limitation, stochastic variational Gaussian processes were developed, which completely remove the dependency of the complexity on the dataset size. This, in effect, allows regression of unlimited data points, which is good for us, because multi-beam data is very dense. Furthermore, this allows us to speed up regression by using stochastic optimization with partial subsets of the data. Among the pre-existing works on informative path planning, scalable approaches optimize paths rather than waypoints, which is how we proceed. However, most of these approaches plan geometric paths, for example splines, rather than simulating the system dynamics as we do in our work. The most promising approaches in completely unknown environments use Bayesian optimization. Bayesian optimization uses an acquisition function, like the expected improvement function shown in this figure, to sequentially sample the function being estimated, in order to reduce the uncertainty of the Gaussian process model and find the optima. There are a variety of well-established acquisition functions that are used throughout Bayesian optimization literature. Recently, however, it was shown that acquisition functions could be learned using reinforcement learning. These learned acquisition functions demonstrated their ability to learn how to exploit the structure of the function being estimated to converge to the optima in much less time, as shown in this figure for several global optimization benchmarks. Furthermore, the structure learned in one context was shown to accelerate learning in another context. This motivates our hypothesis that if we can learn informative path planning behaviors in one environment, then we could use that prior conditioning to plan informative paths in another less accessible environment. Notwithstanding this connection to Bayesian optimization, continuous reinforcement learning has been unexplored in informative path planning literature, despite its ability to generalize, extract implicit information, and improve data efficiency. Reinforcement learning operates under the Markov decision process formalism, described by this figure, where the agent uses its policy to compute actions based on rewards given in certain states. Over time, the agent uses its experiences to improve its policy by maximizing its reward, eventually converging to an optimal policy. So now we try to combine all these elements together to get a reinforcement learning agent that learns to learn its environment. We first started off by experimenting with using stochastic variational Gaussian processes to model a random 2D scalar field with emulated multibeam data acquired from a lawnmower path containing 1,478,000 points. With stochastic optimization, we optimize the hyperparameters of the Gaussian process and its inducing point locations to regress the data, randomly sampling 1,000 points at every optimization iteration. More inducing points, which again approximate the underlying data, means better model capacity, but more resource requirements. This is shown in this figure for different numbers of inducing points, given by n sub ind, where the total variance of the area is given by the trace of the covariance matrix, denoted by sigma, and the time to convergence by t sub opt. The predicted variance and mean are shown on the top and bottom respectively, and the dotted lines represent the sensor coverage. The learned inducing point locations are indicated by the x's in the bottom plots. In an online setting, fully optimizing the Gaussian process at every step would still be too slow, but we can attain a reasonable posterior estimate by partially optimizing the Gaussian process for a limited number of iterations, as we show in this figure with 50 optimization steps at a learning rate of 0.1. As we see again, more inducing points leads to a better model capacity, as indicated by the total variances. We use this to improve the tractability of solving the reinforcement learning problem by partially optimizing the Gaussian process model intermittently and fully at the end. In our experiment, we consider a Dubin's car model for proof of concept, which has as its action a single control input, which governs the rate of turning. The reinforcement learning agent observes the normalized state of this model, the normalized time, and a set of uniformly sampled variances from the Gaussian process. For every step, the agent chooses a heading angle for a lower level controller to follow for delta seconds, 5 seconds in our experiment. After a step, the Gaussian process is stochastically optimized on a random subset of all the prior data gathered along the trajectory, and the normalized reduction in the total predictive variance is given as the reward. If, at any point, the agent drives the car model out of the map area, the episode is ended and a negative reward is given, which has the same magnitude as the maximum achievable reward otherwise. Through this process, the agent should learn to reduce the variance of the Gaussian process in a similar way that a conventional acquisition function does in Bayesian optimization. We trained an agent with the soft actor-critic algorithm to plan informative paths in a completely unknown random field, given the same amount of time as the lawnmower path shown in previous figures. We equipped the agent with a multi-layer perceptron policy with 3 layers of 1,000 nodes and trained it at a learning rate of 1 to the negative 4. We also employed a target action entropy and action noise to encourage the agent to explore its actions and environment more. After about 4,500 episodes taking around 1 hour, the agent started to beat the lawnmower path. After about 30,300 episodes taking around 9 hours, the agent achieved its best policy. After approximately 62,000 training episodes, which roughly took 18 hours, the agent seemingly stabilized on that policy. As the agent learned, it found different policies. Early on, it learned to stay within the boundaries of the area. Shortly after, it started to learn to navigate to areas of higher variance. From there on, it adjusted its policy to reduce as much variance as possible in the given amount of time. In the end, the agent converged to a policy which produces a surveying path that outperforms the lawnmower. The agent accomplished this by observing the incrementally updated Gaussian process model of its environment. Aside from the results shown, we performed a lot of experiments leading up to this. We found that the soft actor critic algorithm, SAC, generally performed much better than the proximal policy optimization algorithm, PPO, which is another state-of-the-art reinforcement learning algorithm. We suspect that this is due to the fact that SAC is an off-policy algorithm, which roughly speaking means that it can use its past experiences to inform its future decisions, whereas PPO is an on-policy algorithm, which only learns over its immediate training episode, leading it to often get stuck in local optima like going in circles as shown in this figure. One drawback of this approach is that the hyperparameters of these algorithms require quite a lot of tuning to get something that actually works. Additionally, we found that training agents over longer time horizons proved to be difficult. We expect that improvements to the agent's policy architectures may improve these issues quite a lot. One possible improvement would be to include a recurrent network in the agent's policy, which could help the agent recognize the dependence of the Gaussian process feedback on previous states and deal with the stochasticity of the reward signal. Another possible improvement is to include a convolutional network in the policy to recognize the spatial correlation between Gaussian process variant samples. These network types are widely used in end-to-end reinforcement learning approaches for Atari games, with quite a lot of success. Additionally, a more principled way to evaluate the Gaussian process posterior and distribute its inducing points may help to increase the informativeness of the reward signal given to the agent. Lastly, pre-training a policy on a large set of optimal paths with trajectory optimization and imitation learning may prove to significantly speed up convergence to an optimal policy. We intend to investigate these things in our future work. If you have any questions or would like to collaborate, please do not hesitate to get in touch. Thank you.